You walk past a 1890s, 1910s downtown bank building, stone facade, heavy cornice, copper-trimmed rooftop silhouette, without ever looking up long enough to notice the one thing that doesn't belong. At the roofline, a short, tower-like finial with ceramic standoffs and multiple metal conductors disappearing behind the parapet. You've been told it's just decoration or just a lightning rod. But decoration doesn't need insulators spaced like electrical isolation, and a lightning rod doesn't usually split into symmetrical multi-lead runs with repeatable mounting geometry. You shift your angle, sun hits the hardware, and you see threaded lugs, clamped terminations, and weathering that suggests long-term current heat exposure, not ornament. So why does a decorative rooftop piece have distribution logic? And why do you find the same silhouette on banks, hotels, and municipal buildings from the same era? Promise, you can trace it, photograph it, and check what period records actually called it. This is not vibes, it's documentation. Walk up to any late 19th century bank building in Chicago's downtown commercial district, those 3 to 5 story stone blocks with heavy cornices and limestone facing, and look up. Really look up. Past the second floor arched windows, past the decorative frieze, all the way to the rooftop edge where the parapet meets sky. There's almost always something there, a small tower, a finial, a vertical element that breaks the roof line, usually centered or placed at corners, often copper-wrapped or bronze-finished, sometimes barely taller than the parapet itself. Tour guides call it Victorian embellishment. Architectural historians label it decorative skyline articulation. Renovation contractors assume it's a lightning rod from an era obsessed with fire prevention. But step across the street, get the right angle when afternoon light hits the metalwork, and you'll see what doesn't fit the explanation. Ceramic insulators, glazed white or brown porcelain eggs, mounted on metal brackets beneath the copper cap. Not one insulator, but several, spaced evenly around the structure's base. Each insulator supports a metal conductor that runs horizontally along the parapet edge before disappearing through precise penetrations in the roofing membrane. The conductors don't converge into a single grounding wire dropping down the building's face, which is what every lightning rod installation does. Instead, they split into parallel runs, each insulated from the masonry, each entering the building at separate points. The hardware isn't ornamental casting, it's threaded lugs, bolted terminations, and compression clamps, the kind of connections designed to be maintained, tightened, and replaced. The weathering patterns around the metal-to-ceramic interfaces show discoloration consistent with long-term electrical contact, subtle oxidation, heat-affected patina, the kind of surface change that occurs when current moves through copper for decades. If this is decoration, why does it need systematic isolation from the building structure? If it's lightning protection, why are the conductors distributed rather than unified into a single ground path? You check the same pattern on a bank 4 blocks away, same tower profile, same ceramic insulators, same multi-conductor routing. Then a third bank, built by a different architect in 1897, same installation geometry, 3 buildings, 3 architects, identical rooftop logic. That's not aesthetic preference. That's specification compliance. Now drop your gaze from the rooftop down to the upper floor cornice line on those same buildings. You're looking for small ceramic mounts, usually white glazed porcelain, sometimes brown stoneware, attached to the brick or stone face just below where the roof structure begins. They're subtle. Most people assume they're remnants of old awning brackets or decorative ironwork supports that were removed during renovations. But compare one of these mounts to a period clothesline bracket or awning support. Different geometry entirely. The ceramic pieces are grooved insulators designed with a deep channel that holds a conductor while preventing electrical contact with the mounting surface. The metal straps that secure them to the masonry aren't decorative at all. They're standoffs keeping the conductor elevated and isolated from moisture paths in the brickwork. On a pre-1920 apartment building in Philadelphia, you can see a string of these insulators running horizontally beneath the eave line, evenly spaced at roughly 30-inch intervals. The conductor they once supported is gone, probably salvaged for copper scrap during a renovation, but the mounting pattern remains. Each insulator is positioned to maintain clearance from the brick surface, and each is placed where water runoff from the roof edge won't create a continuous moisture bridge between the conductor and the building structure. This isn't random hardware, this is high-voltage isolation logic. Compare it to telegraph line insulators from the same era, the kind you see on old utility poles. Same glaze finish, same groove geometry, same intention, prevent current leakage into the support structure. But telegraph insulators are on poles in open air, supporting long-distance communication lines. These are on buildings, integrated into the architecture, routing conductors that clearly originated from the rooftop installations and continued somewhere into the building's interior. Check the placement of these insulators against early electrical codes from the 1890s. The National Board of Fire Underwriters published standards for conductor clearances, specifying minimum distances from combustible materials and requirements for insulation when routing power near masonry. The spacing and mounting patterns on these buildings match those clearance requirements almost exactly. If these were decorative brackets or remnants of non-electrical systems, there would be no reason for the systematic isolation geometry. Clotheslines don't need ceramic insulation. Decorative ironwork doesn't require standoffs to prevent moisture bridging. Signal flag halyards don't follow electrical clearance codes. But a conductor system designed to carry current safely through a building's exterior envelope, moving energy from a rooftop collection point toward interior distribution spaces, would need exactly this kind of installation. The hardware tells you what it was built to do, even when the conductor it supported is long gone. Now, move inside, not into the polished lobby with its marble floors and brass fixtures, but into the spaces most visitors never see: the attic, the mechanical chase, the service corridors that run vertically through the building's core. In an 1890s courthouse in a mid-sized Midwestern town, the kind of municipal building with a central dome, heavy masonry construction, and a warren of service spaces tucked under the roofline, you can still trace the path that those rooftop conductors followed once they penetrated the building envelope. Start at the roof access hatch, climb into the attic space where the timber framing supports the roof structure, and look at the interior surface of the parapet wall, right where those ceramic insulators sat on the exterior face. You'll see paired bolt holes, still threaded where metal brackets were once mounted. The bolt spacing matches the insulator standoff geometry exactly. These weren't random mounting points. They're the interior anchor side of the same system you saw from the street. Follow the alignment downward. On the brick surface between the attic floor joists, there are vertical scars, rectangular impressions in the plaster coating, roughly 6 inches wide, running from the parapet mounting points down toward the main attic floor. These aren't water stains or random damage. They're the footprints of removed conduit or surface-mounted raceways that once enclosed the conductors as they transitioned from exterior to interior routing. At the attic floor level, you'll often find more evidence. Wooden blocks mortared into the brick wall, placed at regular vertical intervals, each block showing screw holes where equipment was mounted, cabinet brackets, junction boxes, regulation or distribution apparatus that has since been removed, but the mounting infrastructure remains. The block placement is systematic, every 18 inches vertically, offset horizontally to create a stable mounting grid. Trace further down into the main building. In the utility corridor on the third floor, there's a vertical chase, a shaft that runs from attic to basement, designed to carry pipes, wires, and service infrastructure. The chase walls show more mounting scars. At one corner, there's a cast iron bracket still bolted to the brick, its purpose now obscure, but its geometry designed to support something heavy and rectangular. A storage cabinet maybe, or a regulation device. Whatever it was, it sat in the vertical path between the rooftop apparatus and the lower floors. Compare these interior traces to the routing patterns in buildings where early electrical systems were installed. When buildings were first electrified in the 1890s and early 1900s, the wiring followed specific paths, from a service entry point through distribution panels along planned routes to avoid fire hazards. The mounting patterns are documented in period installation manuals. What you're seeing in this courthouse matches that systematic logic. If this routing geometry was just leftover renovation debris, you'd expect randomness, arbitrary placement, inconsistent alignment, no relationship between rooftop and interior positions. But the mounting points line up. The vertical chase connects directly to the rooftop penetration points. The cabinet bracket geometry repeats across multiple floors. The building remembers the path the system took, even though the system itself has been removed. Now, broaden your view. Walk through the downtown district of any Great Lakes industrial city, Cleveland, Detroit, Milwaukee, Buffalo, and survey the late 19th century commercial blocks that survived urban renewal. Focus on buildings constructed between 1885 and 1915, when commercial construction boomed, but architectural styles still varied significantly by function and budget. You're looking at bank buildings with stone facades and classical detailing, hotels with brick construction and elaborate cornice work, factories with heavy timber framing and industrial fenestration. 3 different building types, 3 different architectural languages, 3 different sets of design priorities. But go to the rooftop silhouettes, look at the tower structures, the finials, the vertical elements that break the parapet line. Adjust for scale and decorative treatment, and you see the same underlying geometry repeating. A vertical element topped with copper or bronze cladding, surrounded by ceramic insulators at the base, feeding multiple conductor runs that disappear into the building at symmetrical entry points. A bank designed by a prestigious architectural firm in 1891 has it. A working man's hotel designed by a local builder in 1898 has it. A garment factory designed by an industrial engineer in 1905 has it. The decorative treatment varies. The bank's tower is Gothic Revival, the hotel's is Romanesque, the factory's is utilitarian, but the functional hardware is identical, same insulator spacing, same conductor termination method, same rooftop placement logic. Decoration is architect-specific. A Gothic bank doesn't share ornamental vocabulary with a Romanesque hotel, but systems are engineer-specified. If multiple buildings across different design idioms share the same technical installation, that suggests standardization, a common specification, a shared code requirement, or a system class that transcended architectural style. Check the trade publications from that era: the American Architect and Building News, Engineering Record, The Builder, and Woodworker. These journals publish specifications for mechanical and electrical systems, often including diagrams and installation requirements that architects were expected to follow. Lightning protection systems are documented extensively. Single, thick conductor from rooftop rod to buried ground plate, minimal insulation, direct path. What you see on these buildings doesn't match that specification, but other apparatus classes are described in these journals: systems with rooftop terminals, ceramic isolation, and interior distribution networks. The terminology varies: atmospheric apparatus, auxiliary power systems, supplemental collection devices. The language is often generic, which is typical for emerging technologies that haven't yet settled on standardized naming. but the physical requirements are consistent: isolation from building structure, protection from moisture, regulated routing into interior spaces, capacity for maintenance, and part replacement. Photograph 5 buildings from different cities, different architects, different functions. Compare the rooftop installations side by side. If you overlay the images and scale them to the same dimensions, the hardware alignment is nearly identical: conductor spacing within a few inches, insulator placement at the same angular positions, entry points at symmetrical positions relative to the rooftop structure. But that's not coincidence. That's a system class being installed to a common standard. The question isn't whether individual architects invented this feature. The question is, who wrote the specification they were all following? Now consider placement strategy. Not just that the installations exist, but where they're positioned on the building and why. Compare coastal cities, Boston, Philadelphia, Baltimore, cities with telegraph infrastructure and maritime exposure, to inland rail hubs like Indianapolis, Columbus, and Kansas City. The buildings in both regions have these rooftop installations, but the siting logic shows subtle variations that suggest functional optimization rather than aesthetic whim. In coastal cities, the rooftop towers favor positions with clear exposure to prevailing weather patterns, typically the southeast or southwest building corners, where atmospheric conditions arrive unobstructed by neighboring structures. In inland cities, the installations more often sit at the highest point of the rooftop, regardless of corner placement, prioritizing elevation over directional exposure. What kind of system cares about exposure and elevation? Not decoration. Ornament follows symmetry and visual balance, not lightning protection alone. A traditional lightning rod needs height and a direct ground path, but it doesn't need to distinguish between corner and center placement based on regional weather patterns. But a system designed to interact with atmospheric electrical phenomena, capturing ambient charge, collecting weak current from air ionization, or receiving low-power transmission signals, would need exactly this kind of siting logic. Coastal installations face maritime air masses where atmospheric electrical activity concentrates. Inland installations prioritize height to maximize exposure to overhead atmospheric conditions. Check placement against obstruction logic. The towers avoid chimneys and steam vents, even when those features would provide convenient structural support. They avoid positions where roof valleys or adjacent buildings create sky blockage. They're almost never placed where tree canopies or other tall structures would interrupt line of sight to open sky. If this was purely decorative skyline articulation, there'd be no reason to avoid obstructions. In fact, clustering ornamental features near chimneys was common Victorian practice. But if the tower needed unobstructed atmospheric access, the avoidance patterns make perfect sense. Compare this to documented siting requirements in period engineering literature. The 1893 Electrical World Journal includes guidelines for atmospheric apparatus placement, recommending elevated positions, clear sky exposure, and avoidance of steam discharge zones that could interfere with electrical collection. The language is cautious. This was emerging technology, and the publications are describing experimental installations rather than proven systems. But the placement recommendations match what you see on these buildings. Look at the insulators again with placement logic in mind. They're not randomly spaced around the tower base. They're positioned to route conductors away from the tower in multiple directions, creating a distributed collection pattern rather than a single-point discharge. That's not how you protect a building from lightning strikes. That's how you harvest weak current from a large surface area and route it toward a central regulation point. The tower positions itself to interact with the sky. The conductors distribute the collection across the rooftop perimeter. The interior routing brings everything together at a point where regulation, storage, or distribution can occur. If it's decorative, why does every installation choose the best atmospheric exposure over the most visually prominent location? If it's standard lightning protection, why does it avoid the simplest structural mounting points in favor of optimal sky access? The buildings are sited like collection apparatus, not ornament. Now move back inside, but this time into the service cores of pre-1910 hotels, the grand downtown establishments with 300 rooms, electric lighting retrofitted in the late 1890s, and complex infrastructure hidden behind decorative plaster and wood paneling. These buildings are archives of layered technological change. You can see gas pipe remnants from the original 1880s lighting, early electrical conduit from the 1895-1900 retrofit, telephone backboards from the 1905-1910 expansion, and underneath it all, traces of something older that doesn't fit any of those categories. In the basement mechanical room of a Chicago hotel built in 1892, there's a brick wall near the main electrical service entry. On that wall, a rectangular impression in the plaster, about 30 inches tall and 18 inches wide, with 4 cast-iron mounting brackets still bolted to the brick at the corners. The brackets are heavy-duty, designed to support significant weight, and they're not positioned like electrical panel mounts, which typically hang at eye level for maintenance access. These are mounted low, about 3 feet off the basement floor, where a cabinet or apparatus could rest on the ground while being secured to the wall. Compare this footprint to known systems. Telephone equipment from that era used wooden backboards, typically 12 inches wide, mounted vertically at comfortable working height. Early electrical distribution panels were metal-enclosed boxes, shallow profile, mounted at 5 to 6 feet for safety. What was here wasn't shallow and wasn't at working height. The mounting pattern suggests something more substantial, a deep cabinet, possibly with internal compartments, heavy enough to need floor support in addition to wall anchoring. Trace the wall upward. Above the cabinet footprint is a vertical conduit chase, a plastered-over channel running up through the ceiling and into the floor structure above. The chase alignment is offset from the main electrical service routes, which run along the opposite wall toward the elevator machinery room. This chase goes in a different direction entirely, toward the building's southwest corner, where the rooftop tower installation sits 5 floors above. On the 3rd floor, in a service corridor closed to guests, you find more evidence. The corridor ceiling has a plastered-over access panel. You can see the seam where the panel was cut and later filled, positioned directly below the vertical chase, a maintenance access point placed where the vertical routing intersected a major floor. Lift your eyes to where the chase continues upward and you see porcelain knob remnants mortared into the brick wall, the kind of insulating spacers used in early electrical installations to keep conductors away from combustible surfaces, but sized larger than typical lighting circuit hardware. Now compare this routing geometry to documented electrical retrofit patterns from the 1890s. Hotel engineers recorded their installations meticulously because fire insurance rates depended on demonstrating code compliance. The electrical service entry was mandated by code to be near the street-facing wall, close to utility company connections. Distribution panels were required to be in accessible locations with clear labeling. Circuit routes followed prescribed paths to minimize fire risk. What you're seeing doesn't follow those patterns. The cabinet footprint is in the wrong location for main electrical service. The vertical chase routes away from the primary distribution zones. The conductor sizing suggests heavier current capacity than lighting circuits needed, but lighter than motor power feeds. If this was telephone infrastructure, the routing would target guest room floors and the front desk, not a basement corner and a rooftop tower. If it was supplemental electrical service, the distribution logic would mirror the main system's layout. But if it was a distinct system, one that collected something from the rooftop, regulated or stored it in basement apparatus, and distributed it selectively to interior loads, then the routing pattern makes sense. The rooftop tower captures and sends downward. The basement cabinet regulates and prepares for distribution. The vertical chase connects the two, bypassing the main electrical infrastructure because it's serving a different function. The building shows you a parallel grid that ran inside the walls alongside the known systems but never quite merged with them. Now anchor this investigation with specific examples. Take 3 buildings in 3 different cities, each representing a different building class, each showing the same trio of physical evidence: rooftop apparatus, ceramic isolation hardware, and interior routing traces. First, the First National Bank building in Milwaukee, built 1893 stone construction, 5 stories, classical revival detailing. The rooftop has a copper-clad tower at the southwest corner, approximately 4 feet tall, with 6 ceramic insulators visible at the base. The insulators support conductor remnants, corroded copper straps, that once ran horizontally along the parapet before entering the building through sealed roof penetrations. Inside, the 4th-floor attic space shows bracket mounting points on the brick wall directly below the rooftop tower position, and a vertical chase runs down through the building core toward the basement. The 1894 city permit records list electrical apparatus installation as part of the building's systems, separate from the lighting circuit permit, filed in 1896. Second, the Tippecanoe County Courthouse in Lafayette, Indiana, built 1884, expanded 1902. The expansion included a rooftop installation, copper-topped finial on the main dome, ceramic insulators mounted on copper straps, conductor routing visible in the attic space. The county maintenance logs from 1905-1918 include line items for insulator replacement and conductor repair, with procurement records showing ceramic parts ordered from electrical supply catalogues, not architectural ornament suppliers. The maintenance entries stop after 1918, and a 1922 renovation contract includes language about removal of obsolete rooftop apparatus. Third, the Sterling Loft building in Cleveland, built 1889, converted from factory to commercial office space in 1905. The building has a utilitarian rooftop structure, no decorative cladding, just a galvanized metal housing with visible conductor terminations and insulator mounts. The interior shows the most intact routing evidence of the 3 buildings, a complete vertical chase from roof to basement, with cast iron cabinet brackets still in place on the 2nd floor and basement level. The original factory blueprints from 1889 don't show the rooftop apparatus, but the 1905 conversion drawings include a note: atmospheric terminal and associated distribution infrastructure to remain in service. 3 buildings, 3 cities, 3 different original functions, but the same physical signature: rooftop collection point, insulated conductor routing, interior distribution preparation. The documentation across all 3 uses similar language, not decorative finial or lightning rod, but apparatus, terminal, distribution infrastructure. Period procurement records list ceramic insulators alongside electrical hardware, conduit fittings, conductor clamps, junction boxes, not alongside architectural ornament. Maintenance logs describe repairs and part replacements using technical terminology consistent with electrical or atmospheric systems, not aesthetic upkeep. Now check what's documented versus what's missing. All 3 buildings have clear records of the rooftop installations being maintained between 1895 and 1920. All 3 have records of decommissioning or obsolescence language appearing in the early 1920s. All 3 show physical evidence of removal, cut conductors, missing cabinets, sealed routing chases, but the rooftop towers remain reinterpreted as decorative elements. The paper trail points to a system class that was installed, maintained, and then intentionally removed, not decoration that fell out of fashion, not lightning protection, which these buildings also had in the form of traditional grounded rods, something distinct that was functional long enough to require documented maintenance, prevalent enough to appear across building types and regions, but ultimately obsolete enough to be systematically decommissioned. If you want to verify this pattern yourself, these are the documents to request from city archives: building permits listing apparatus installation or electrical equipment separate from main power service. Maintenance procurement records showing insulator and conductor purchases. Renovation contracts describing removal of rooftop or attic systems. Insurance inspection reports mentioning rooftop terminals or auxiliary equipment. The buildings are real. The mounting hardware is still there. The documentation exists in city archives and historical society collections. This isn't speculation about what might have been. This is verification of what's observable and what's recorded. The pattern repeats. The physical evidence converges. The documentation classes align. Multiple independent sites pointing to one interpretation. A standardized system that once served a function, maintained its presence long enough to leave both physical and documentary traces, and then disappeared from institutional memory while its hardware shells remained on the rooftops. Now make the terminology shift that changes how you search the archives. Stop looking for decoration or lightning rod and start looking for what period engineering literature actually called these installations. The language matters because once you know the right terms, entire categories of documentation become visible. In the 1892 Electrical Engineer Journal, there's a technical note describing rooftop installations for commercial buildings, atmospheric terminals with insulated conductor arrangements for auxiliary collection purposes. Not decoration, not standard lightning protection, a distinct category. The article describes ceramic insulation requirements, conductor sizing for low current applications, and mounting specifications for exposure to weather while maintaining electrical isolation. In the 1897 Lightning Rod Conference proceedings, a gathering of electrical engineers and building inspectors discussing electrical safety standards, there's a section distinguishing between direct protection systems, traditional lightning rods with single heavy grounding conductors, and atmospheric apparatus for supplemental purposes, multi-conductor installations with interior routing and regulation components. The distinction is explicit. The former protects against strikes, the latter interacts with ambient atmospheric electrical conditions. Trade catalogues from the period show the hardware. The 1895 catalogue from Chicago Insulator and Equipment Company lists atmospheric collection insulators as a distinct product category, separate from telegraph insulators and power line insulators. The catalogue shows ceramic eggs with specific groove geometry, rated for low current atmospheric applications, sold in sets with matching conductor clamps and mounting hardware. The product descriptions include installation guidance for rooftop terminals requiring electrical isolation from building structure. Building codes from the same era reflect awareness of these systems. The 1899 National Building Code includes a section on auxiliary electrical apparatus, requiring that any rooftop installations beyond standard lightning protection must use approved insulation, maintain specified clearances from combustible materials, and include accessible disconnection points. The code doesn't mandate these installations, they're optional, but it regulates them, which means they were common enough to need standardization. Patent filings from 1885 to 1905 show inventors proposing various designs for atmospheric electrical collection, storage, and distribution systems. The patents describe rooftop terminals, insulated conductor networks, regulation apparatus, and interior distribution methods. Most of these patents describe experimental systems that were never widely commercialized, but the sheer volume of filings indicates significant interest in the technology class. The hardware described in the patents, ceramic insulators, multi-conductor routing, cabinet-mounted regulation devices, matches what you see on the buildings. Once you have the terminology, the archive stops being silent. Search City Building records for atmospheric apparatus permit instead of lightning rod permit, and you find separate filing categories. Search maintenance budgets for insulator replacement or terminal repair, and you find line items distinct from electrical service or lightning protection costs. Search insurance inspection reports for auxiliary equipment or rooftop collection apparatus, and you find descriptions of installations that don't fit the traditional protection or ornamentation categories. The language used in these records is often generic and cautious, which is typical for emerging technologies. Terms like apparatus, auxiliary, supplemental, and atmospheric are vague by design. Engineers were documenting systems that were still being refined, and they avoided over-promising capability, but the physical descriptions are precise: ceramic insulation, multi-conductor arrangements, interior routing to regulation points, capacity ratings for low-power applications. Compare this documentation language to how the same features are described in modern architectural surveys. Today's building historians call them decorative finials or Victorian rooftop ornament. Preservation guidelines classify them as non-functional architectural elements to be maintained for historical aesthetics. The functional terminology, terminals, insulators, conductors, regulation apparatus, has been replaced by generic aesthetic labels. The shift in language represents a shift in understanding. The original installers and maintainers knew these were functional systems and documented them as such. Later generations, encountering the remnants after decommissioning, saw unfamiliar hardware and defaulted to assuming ornamental purpose. But the period records preserve the original interpretation. When a 1903 maintenance log lists replacement of 3 atmospheric collection insulators on courthouse rooftop terminal, that's not decorative upkeep. When a 1908 procurement order specifies ceramic insulators rated for auxiliary current applications, quantity 12, that's not ornament supply. When a 1914 building permit notes removal and disconnection of obsolete atmospheric apparatus, that's not renovation of architectural detailing. The names in the records change what you see on the rooftops. A decorative finial becomes a collection terminal. Random ceramic mounts become insulation points for conductor routing. Victorian skyline articulation becomes standardized apparatus placement following engineering specifications. The hardware hasn't changed. Only the language describing it has shifted, and with that shift, the functional interpretation got erased from institutional memory, even though the documentation proving that interpretation still exists in the archives. Now address function directly, but with appropriate constraints. What could a system like this actually do, given the technology and electrical understanding of the 1890s-1910s era? The answer requires acknowledging both the possibilities and the significant limitations of atmospheric electrical collection during this period. First, the power capacity was inherently low. Atmospheric electrical phenomena, ambient charge in air, potential differences between Earth and upper atmosphere, weak current from ionization, could be detected and accumulated, but the available energy was minimal compared to what early electrical grids provided. We're talking about milliamps to low amps at modest voltages, not the multi-kilowatt loads that motors or arc lights required. Any functional application had to match this power constraint. Second, the collection was intermittent and unreliable. Atmospheric electrical conditions vary by weather, time of day, and seasonal factors. A system dependent on atmospheric collection couldn't provide baseload power or serve critical loads. It could only supplement primary power sources or serve applications that tolerated interruption. Given these constraints, what loads make sense? Period engineering literature suggests several plausible applications: indicator lighting, low wattage lamps for signaling, safety lighting, or night indicators. Early carbon filament bulbs operated at 2–4 watts, well within the capacity range of modest atmospheric collection. Hotels used indicator lamps in corridors, stairwells and service areas, non-critical lighting that could tolerate variability. Instrument power, electrical measuring devices, clocks, telegraph sounders, and early detection equipment. These applications required minimal sustained power and could function intermittently. Battery charging. Accumulator cells that stored collected charge for later use, smoothing the intermittent collection into more stable supply. Period electrical literature describes supplemental charging methods for small battery banks, particularly in buildings that maintained emergency lighting or signaling systems. Signaling support, auxiliary power for building communication systems, call boxes, or alarm circuits, not primary power but backup or supplemental supply that extended battery life or reduced maintenance frequency. These applications share common characteristics: low power demand, tolerance for interruption, supplemental role rather than primary supply. None of them are transformative or grid replacing, which aligns with why the technology was eventually abandoned. Once reliable electrical grid scaled, even these modest supplemental applications became easier to serve through standard utility connections. Now, tie function back to physical evidence. The rooftop terminal's siting, elevated position, clear sky exposure, distributed conductor collection matches what an atmospheric collection point would need. The ceramic insulation and conductor routing, designed for low current but requiring careful isolation from building structure, matches the characteristics of weak atmospheric electrical flow, which could leak through insufficient insulation despite low power levels. The interior cabinet footprints, substantial mounting, accessible maintenance points, positioning near service areas, match what regulation, storage, or distribution apparatus would require. Check what period codes restricted. Early electrical codes mandated heavy insulation standards, strict clearance requirements, and accessible disconnection points, not because the systems were high power, but because electrical technology was new and safety standards erred toward caution. The buildings show compliance with those requirements: insulated routing, clearance maintenance, accessible junction points. This suggests the installations were code-recognized and inspector-approved, not experimental bootleg systems. Also check what engineers warned about. Period literature cautions that atmospheric collection systems required frequent maintenance, were sensitive to weather damage, and provided unreliable output. These warnings align with what maintenance records show: regular insulator replacements, conductor repairs, and eventual descriptions of installations as troublesome or obsolete. The function was plausible but marginal. It worked well enough to be maintained for 2 to 3 decades across multiple building types and cities. It was useful enough to appear in building codes and trade catalogues, but it was never essential enough to survive once more reliable alternatives became available. If atmospheric collection could have replaced grid power, it would have. It didn't, which tells you it was always supplemental, always limited, always competing with more robust alternatives. The fact that it disappeared isn't mysterious, it's economically rational. Grid power scaled, prices dropped, reliability improved, and maintenance simplified. An atmospheric collection system that required rooftop apparatus, ceramic insulator upkeep, interior cabinet maintenance, and conductor inspection couldn't compete with plugging into a utility service that delivered reliable power on demand. The installations weren't magic. They were marginal utility electrical systems that briefly made sense in an era when grid power was expensive, unreliable, or unavailable in some locations. They served modest loads, required significant maintenance, and became obsolete as soon as better options arrived. Plausible doesn't mean revolutionary. Functional doesn't mean transformative. The system could work, did work, for a limited time and purpose, and then rationally disappeared when infrastructure evolved. The physical evidence shows you a system designed for function. The documentation shows you engineers taking it seriously. The maintenance records show you sustained operation. And the disappearance shows you economic reality. When a better solution arrives, marginal technologies get replaced, no matter how interesting their engineering. Now examine how maintenance reality creates the documentary fingerprints that prove function. Decoration gets preserved or discarded based on aesthetic value, but systems generate parts, logistics, procurement records, and repair documentation that follow engineering necessity, not architectural preference. Start with the replacement patterns. In the maintenance logs for the Tippecanoe County Courthouse, those records mentioned earlier, the entries for insulator replacement appear roughly every 18 to 36 months between 1905 and 1918. The replacements aren't cosmetic. The procurement notes specify technical requirements. Ceramic insulators, high voltage type, grooved for conductor retention. The quantities vary, sometimes 3 replacements, sometimes 6, suggesting that failures occurred from environmental exposure rather than wholesale system upgrades. Compare this to how decorative elements were maintained in the same building. The cast iron ornamental railings on the courthouse steps were repaired once in 25 years, welded crack repair in 1909. The copper roof finials were cleaned but never replaced. Decorative maintenance follows damage events, not scheduled intervals. System maintenance follows wear patterns and operational necessity. Now look at the physical evidence of replacement. On a pre-1910 hotel in Detroit, the rooftop installation shows 3 different generations of ceramic insulators. 2 original brown glazed units remain on the north side, weathered but intact. 4 white glazed replacement units on the south and west exposures. These match catalogue designs from 1905-1915 indicating midlife replacement, and 2 modern reproduction insulators on the east exposure installed during a 1990s preservation effort by contractors who thought they were maintaining historical decorative hardware. 3 generations, 3 distinct product styles. That's maintenance history written in ceramic and glaze. If these were purely decorative, there'd be no functional reason to replace weathered units. Aged ornament acquires patina value. But if the insulators served an electrical isolation function, degraded units would need replacement to maintain system safety and performance. Ceramic cracks, glaze deteriorates, and insulation integrity fails. Replacement wasn't optional. Check procurement sources. The 1911 maintenance budget for the Milwaukee Bank building includes a line item: electrical hardware, atmospheric system repair, $47 was. The invoice detail lists parts purchased from Chicago Insulator Company: 6 ceramic insulators, 12 conductor clamps, copper wire stock. These aren't architectural supply house purchases. They're electrical component orders from specialized vendors. Compare this to lightning rod maintenance from the same era. Lightning protection systems, once installed, required minimal upkeep, periodic ground connection inspection, rare conductor replacement if damaged. The maintenance intervals were measured in decades, not years, but the atmospheric apparatus installations show frequent parts replacement, suggesting active use and environmental stress rather than passive protection sitting idle until needed. Now look at what happens when maintenance stops. In multiple buildings, you can identify the moment when upkeep ended by examining insulator conditions. Units that failed after maintenance ceased were never replaced. They remain cracked or missing, leaving empty mounting brackets. Conductor ends show cut marks rather than corrosion patterns, indicating intentional disconnection rather than natural deterioration. Roof penetrations were sealed with mortar or roofing cement, blocking the routing paths the conductors once followed. This is decommissioning, not neglect. Someone made decisions about what to remove, what to seal, what to leave in place. The valuable copper conductors were salvaged, they had scrap value. The ceramic insulators were sometimes removed, sometimes left as empty shells, no material value, but taking them down required labor. The rooftop towers stayed, because removing them would have required cutting into the roof structure and risking water infiltration. Check decommissioning documentation. The 1922 renovation contract for the Tippecanoe County Courthouse includes this language. Remove and dispose of obsolete atmospheric apparatus from rooftop and attic spaces. Disconnect and remove interior conductor routing. Seal all roof penetrations. Rooftop terminal structure may remain for architectural continuity. That's not vague renovation language. That's a specific scope of work describing a known system class being intentionally removed. The maintenance records are evidence of sustained operation. Parts don't get replaced unless they're being used. Procurement doesn't follow technical specifications unless performance matters. Repair intervals don't reflect wear patterns unless the system is active. And decommissioning language proves these weren't decorative misunderstandings. You don't write remove obsolete apparatus for Victorian ornament. You don't specify disconnect conductor routing for decorative metalwork. The contractors who removed these systems in the 1920s knew exactly what they were removing. They described it accurately in their work orders, priced the labor accordingly, and salvaged the valuable components. The maintenance records are the fingerprints of function. They show systematic upkeep following engineering logic, parts replacement matching operational wear, and decommissioning that treated these installations as systems, not aesthetics. When you find a building with 3 generations of insulators still in place, you're not looking at decoration that was randomly maintained. You're looking at a system that was actively used, carefully maintained, and eventually abandoned when better alternatives made its operation unnecessary. The records and the hardware tell the same story. These installations were functional long enough to develop maintenance routines, wear out components, require parts logistics, and justify the cost of upkeep. Until they didn't. Now compile the verification method into a practical checklist. If you want to investigate this yourself, identify installations, document physical evidence, and trace the paper trail, here's how you structure the investigation. Start with site selection. Focus on commercial buildings constructed between 1885 and 1915 in cities with preserved downtown cores, banks, hotels, courthouses, and municipal buildings are your primary targets. These building types attracted capital investment in supplemental systems and generated the most complete documentation. Avoid heavily renovated structures where rooftop work has eliminated original hardware. Visual survey checklist. What to photograph. Rooftop silhouette from street level, capturing the full tower finial profile and its position relative to the building edges and corners. Close detail of rooftop hardware, including any visible conductor terminations, mounting brackets, or metalwork that shows threaded connections rather than cast ornamental detail. Ceramic insulators, if accessible, showing glaze condition, groove geometry, and mounting method. Compare the shape and size to known telegraph or power line insulators. Roof penetration points where conductors entered the building. Look for sealed holes, patched roofing, or remaining conduit entries near the rooftop apparatus position. Interior routing traces in attic spaces, bracket mounting holes, vertical chase scars, cabinet footprints on brick walls, any remaining hardware that suggests distribution or regulation apparatus, conductor remnants or mounting evidence on exterior walls below the roofline, particularly near corners or along cornice lines where insulators would have provided clearance. Comparative installations on multiple buildings. Document at least 3 separate examples to establish pattern repeatability. Each photograph should include scale reference, a measuring tape, a standard brick course, your hand, so that hardware sizing and spacing can be measured later. Documentation research checklist, what to request from archives, building permits filed during original construction, and any major renovations between 1890 and 1925. Look for language describing electrical apparatus, atmospheric equipment, auxiliary systems, or rooftop terminals. These terms appear in permit files separate from standard electrical service or lightning protection permits, maintenance and procurement records, especially from municipal buildings where budgets and expenditures were documented. Search for line items mentioning insulators, conductors, terminal repair, or rooftop apparatus. Note the procurement sources. Electrical supply vendors indicate functional system, architectural suppliers indicate ornament, insurance inspection reports. Fire insurers documented building systems extensively, including unusual electrical installations. Period reports often describe rooftop hardware with technical terminology that reveals functional interpretation, architectural specifications from original construction. For buildings designed by documented architects, check if the specification books survive in historical society collections. These specs sometimes include sections on auxiliary equipment or special electrical provisions that describe non-standard installations, renovation and modernization contracts from the 1920s, 1940s. Look for language about removal, obsolescence, or decommissioning applied to rooftop or attic systems. These contracts often itemize what was removed and why. Trade journals and technical publications from 1890-1920. Search electrical engineering journals, builders' magazines, and municipal engineering proceedings for articles about atmospheric apparatus, auxiliary collection systems, or supplemental electrical installations. Patent filings can provide technical context. Search USPTO records for patents filed 1885-1910 related to atmospheric electrical collection, building-mounted terminals, or auxiliary power systems. Even if specific buildings didn't use patented designs, the patents document what system categories engineers were developing. Comparative analysis framework, distinguishing system from ornament, create a comparison matrix. Column 1, traditional lightning protection specifications. Single conductor, heavy gauge, direct ground path, minimal insulation. Column 2, decorative finials, cast ornament, no electrical hardware, purely aesthetic siting. Column 3, your documented observations, multi-conductor, ceramic insulation, interior routing, systematic placement. If your observations align with column 3, but not columns 1 or 2, you've documented something distinct from both lightning protection and decoration. Measure repeatability. If you find the same hardware configuration on buildings from different cities, different architects, and different construction years, you've eliminated architect-specific aesthetic choice and established system-level standardization. Check maintenance patterns. If replacement parts were procured from electrical suppliers rather than architectural ornament vendors, and if replacement followed functional wear patterns rather than aesthetic damage repair, you've established operational use rather than decorative presence. Verification without speculation. When you present findings, distinguish between what's directly observable. Hardware exists, mounting patterns repeat, documentation describes apparatus, and what requires interpretation, specific function, power capacity, reason for obsolescence. State uncertainties clearly. If insulator types vary between buildings, note that variation and acknowledge you don't know if it represents different system generations, regional supplier differences, or replacement with available parts. When documentation uses generic terms like auxiliary apparatus without detailed functional descriptions, present that ambiguity. Don't force definitive conclusions from incomplete records. If experts disagree about interpretation, architectural historians calling it ornament, Electrical engineers, seeing system logic, present both perspectives and explain why the physical evidence supports one interpretation more strongly. The goal isn't to prove a single, definitive explanation. The goal is to document a pattern that challenges the default decorative label and demonstrates that these installations were more than architectural embellishment. The investigation is reproducible. Any researcher with archive access and a camera can follow this method, document the same patterns, and reach independent conclusions. That's how evidence-based investigation works, not revelation, but systematic observation and documentation that others can verify or challenge. The buildings are still there, the hardware remains, the archives exist. This isn't about recovering lost secrets. It's about reading what's already visible and checkable once you know what to look for. The removal followed a predictable sequence, documented across multiple buildings with remarkable consistency. First, the decision to decommission appears in municipal or corporate budgets, usually during facility modernization projects, when buildings were being upgraded to accommodate expanded electrical service or improved HVAC systems. The language in these budgets is revealing: removal of obsolete auxiliary electrical apparatus, disconnection of outdated rooftop equipment, or simply atmospheric system decommissioning. The physical removal happened in stages driven by salvage economics. The copper conductors came out first. They had immediate scrap value. The interior cabinets followed. Cast iron and any remaining copper components could be sold. The ceramic insulators might stay or go depending on accessibility and labor costs. They had no material value, so removal was pure expense. The rooftop towers almost always remained because taking them down required cutting into the finished roofline and risking structural damage or water infiltration. It was easier and safer to leave the architectural shell while stripping the functional core. This created the palimpsest that survives today. The most visible element of the system, the rooftop tower, remains in place, while all the evidence of its original function has been carefully removed from beneath it. Looking at the building from the street, you see what appears to be ornamental architecture. Only when you trace the scars inside the building do you realize that ornament once connected to a complete interior infrastructure that's now absent. Compare decommissioning scars across multiple sites. On the Milwaukee Bank building, you can see where conduits were removed from attic walls, rectangular chases now filled with different colored plaster, indicating repair work. In the Cleveland factory building, the cabinet mounting blocks remain, but the cabinets themselves are gone, leaving bolt holes that tell you the dimensions and weight of what was removed. In the Indianapolis courthouse, the rooftop conductor penetrations were sealed with concrete patching compound that's clearly 20th century material, different from the original 1890s masonry. The buildings show you the moment of transition. These aren't random renovation artifacts, they're the systematic evidence of a technology class being retired. Walk past that same 1890s bank building now. The rooftop tower is still there. Copper-clad finial, stone base, carefully preserved through multiple renovations. The preservation guidelines classify it as character-defining historical architecture. Tour guides point it out as an example of Victorian decorative skyline articulation. The building's historical designation protects it from removal, but the copper conductors that once ran from that tower along the parapet edge are gone. The ceramic insulators that held those conductors are empty shells or entirely missing. The interior routing paths are sealed. The basement cabinet space now holds electrical panels for modern building systems. So the vertical chase that once connected rooftop to basement has been repurposed for modern data cabling, its original function forgotten. What remains is the most visible component of a system that no longer exists. The rooftop tower stands because it became architecture, redefined, reclassified, reinterpreted. The rest of the system disappeared because it remained infrastructure, and obsolete infrastructure gets removed. This is the architectural palimpsest, one technology erased by another, but leaving enough traces that careful observation can reconstruct what stood there before. The building remembers through mounting scars, bracket footprints, and routing geometry, even when human memory and institutional records have moved on. The system wasn't imaginary, it was installed, documented, maintained, and eventually decommissioned following a logical economic sequence. Utility grids became reliable and inexpensive, making atmospheric collection uncompetitive. Maintenance costs for rooftop systems exceeded the value of their output. Standardization favored centralized power distribution over distributed supplemental sources. Obsolescence followed predictably, but obsolescence erases technical knowledge. Engineers who installed these systems retired. Maintenance workers who understood their function moved to new technologies. Trade journals stopped publishing technical details about apparatus that no one was specifying anymore. Patent categories that once described atmospheric collection hardware disappeared from classification systems. Documentation survived in archives, but without the technical vocabulary to search for it, the records became invisible. You can still verify this. Photograph the rooftop towers. Trace the interior routing scars. Request the maintenance records. Search period catalogues for ceramic insulators and rooftop terminals. Check renovation contracts for decommissioning language. Compare installations across multiple buildings to establish pattern repeatability. The evidence exists, physical and documentary, waiting for anyone willing to look systematically. Just decoration is the label given to technology that outlasted its context. The hardware hasn't changed, the buildings haven't forgotten. Only the interpretation shifted, replacing engineering terminology with architectural simplification. What remains on those rooftops isn't ornament that mimicked function. It's function that became ornament once the rest of the system was stripped away.